Global Positioning System GPS. The current system, which we call as GPS, Navstar GPS, is managed by US Air Force for DOD, and the current system became fully operational in June 26, 1993, when the 24th satellite was launched. GPS provides specially coded satellite signals that can be processed with a GPS receiver, enabling the receiver to compute position, velocity and time. So a minimum of 4 GCS satellite signals are required to compute positions in 3 dimensions and the time of offset in the receiver clock. Accuracy and precision of data that increases with more satellites you have. There are 3 parts in global positioning systems: space segment, control segment, and finally the user segment, the receiver. Space segment, the GPS uses a constellation of 24 satellites that orbit Earth at this height around 2 times a day, and the orbital position is constantly monitored and updated by the stations on the ground, and each satellite is identified by number and broadcasts a unique signal. The signal travels at a speed of light, and each satellite has a very accurate atomic clock of these seconds. Since the GPS receiver calculates its location by trial iteration, the task is to determine its distance from the multiple satellites it has locked. So the GPS system uses 2 types of signals to calculate distance. One is code phase ranging, the other is carrier phase ranging. Code phase ranging: each satellite has a unique signal. It continuously broadcasts its signal and also sends out a timestamp every time it starts. So the receiver has a copy of each satellite signal, and it determines the distance by recording the time between the satellite says it starts its signal and when the signal reaches the receiver. So this is the time shift: send signal and receive signal. So distance is calculated by a simple formula, which is velocity is equal to distance by time, and distance is calculated by velocity into time. So if the system knows the velocity of the signal and the time it takes for the signal to travel from the sender to the receiver, the distance between the sender and the receiver can be determined. And talking about carrier phase ranging, the surveying quality receivers use this underlying carrier frequency. So easy to determine the number of cycles, and the proportion of the partial cycle is difficult to determine. So this is called some phase ambiguity, and phase ambiguity error is resolved by comparing multiple signals from multiple receivers. So it is more precise system. And when we talk about receiver, the receiver collects, decodes and processes the satellite signals, and the basic receiver does not include a transmitter. The different level of positions are available. The receiver determines its location by trial iteration. So what is GPS trial iteration? Each satellite knows its position and its distance from the center of the Earth. This is how the Earth is, and this is the satellite, and the distances are known. So each satellite constantly broadcasts its information. With this information and the distance, the receiver calculates its position. The distance to one satellite does not mean that it has provided enough information. So when the receiver knows its distance from only one satellite, its location could be anywhere on the Earth's surface, that is an equal distance from the satellite, represented by this circle. And the receiver must have additional information. So with signals from 2 satellites, the receiver can narrow down its location to just 2 points on the surface when the 2 circles intersect. See, this is 1, this is 2 circle. Now these are the 2 points where the receiver can be. This is a different illustration, And knowing it from 3 satellites, the receiver can determine its location because there is only 2 possible combinations and one of them is out in a space. So this is how the third satellite emphasizes or points the exact location. So in this example we can see that the receiver is located at certain point B, this point, and the more satellites being used, the greater the potential accuracy of finding the exact location. So what are the factors influencing the positional accuracy? The number of satellites the receiver can track, the number of channels the receiver has its part of its design. The higher the number of channels, the greater the potential accuracy. The higher the number of channels, the greater the cost, and the number of satellites that are available at that particular time. Since because of the way the satellites orbit, the same number are not available at all times. So when planning precise GPS measurement, it is far important to check for the satellite availability, location, and the time of measurement. Large number of channels are required, that means 6 to 10. At the time the measurement, the number of available was less than that, the data will be less accurate. And finally, the number of different systems that the receiver can track, that is VAS, wide area augment, GLONASS or others. So the system errors that are occurring during the time the receiver is operating, it may be the GPS system have several errors itself that have potential to reduce the accuracy, and to achieve high level of precision, differential GPS must be used. Differential GPS uses one unit at a known location and a rover moving one. The stationary unit compares its calculated GPS location with the actual location and computes the error. Now this error is reduced. So the rover data is adjusted for the error, real-time kinematic and post-processing. And talking about the location, once the GPS receiver has located its position, it is usually displayed in one of the 2 common formats, latitude and longitude and UTM. So coming to ground segment, the ground segment has 1 master control, 1 alternative master control station, 12 command and control antennas, and 16 monitoring sites, all distributed like this in the globe. And GPS errors include satellite geometry, satellite orbits, multipath, atmospheric effects, clock, and satellite geometry creates error like describing the position of the satellites with each other. The best geometry and the least error occurs when the satellites are equally distributed, which is we call as dilution of precision. Satellite geometry errors occurs when the satellites are concentrated in just one quadrant or in a straight line, and the PDOP, that positional dilution of precision, is an indication of the quality of the 3D coordinate satellite geometry. So the satellite geometry error is not measurable. It trends to enhance other errors, and the error which is caused by the orbits, even though the satellites are positioned in very precise orbits, some shift are possible due to gravitational influences, and orbit error can be order of 2 meters. And the multipath errors are caused by satellite signals reflecting off different objects, and it increases chance of occurrence when around tall buildings. And atmospheric errors may be the radio signals travel at a speed of light in space but are slowed down by the atmosphere, and the majority of this effect can be inhibited by the receiver. Like lower frequency signals are slowed down more than that high frequency, or the receiver can determine the difference in the arrival time of high and low frequency signals and calculate a correction. And clock error, since the synchronization of the satellite and receiver clocks, small amount of inaccuracy in timing remains, and this can result to an order of 1 meter. So to keep the clock errors to 1 meter or less, the time error must be limited to only 20 to 30 nanoseconds. How to use GPS? We have availability, because GPS satellites are not stationary above one point, they're moving. Like communication satellites, the number of satellites available at any one time is not constant. Satellite availability should be checked before scheduling GPS service, especially when the high precision is required, or that some stations may be partially blocked. This is one of the site, And example of selective availability for GPS and GLONASS. These are the numbers. You can have a look on it. And coming to GNSS, the Russian GNSS, as the size of the area increases, the dilution of precision increases. The dilution of precision is given in multiple measurements. GDOP, geometric dilution of precision, a combination of navigational position and the time error. And PDOP, the positional dilution of error, the spatial geometric quality of the positional solution. And HDOP is horizontal dilution of precision, the measure of the quality of the horizontal position. And VDOP, vertical dilution of position, measure of the quality of the vertical position. And TDOP, time dilution of position, means error of the time estimation. So these are the DOP numbers. If one ideal, 20, 50, it's poor. So values below 2 will produce acceptable result for most surveys, surveying and other applications. So values over 3 should not be used. Static time, because the receiver continuously calculates its position, increasing the time it is stationary improves the precision. And static time can be divided into 3 categories: static, fast static, and kinematic. So static are the recommended time is related to the distance between the surveying, and static times of 30 minutes to 2 hours recommended for distance of 1 to 20 miles. To qualify for static survey, both receivers must observe a minimum of same 4 satellites for the duration of the time, and data is post-processed after that. Static surveys have the highest precision and can be used for any surveys. And coming to fast static, it uses the same procedure as static surveys, just shorter observation times. 5 to 10 minutes are usually sufficient for surveys that do not require the highest level of precision. RTK requires 2 receivers recording observations simultaneously, and RTK requires a receiver that can use the dual frequency element for observations, can lock on to satellites while on the move, must have a radio link to transfer data and calculate error in real time, and accuracy can be as good as 0.02 to 0.05 feet. So thank you so much. Hope you got an idea of what is GPS.